All right, in this video, we're going to talk about changes in motion. So let's look at a couple pictures, and then we're going to watch a time warp video, which is kind of cool. So you exert a force on an object. So you exert a force on a baseball when you throw it, when you catch it, when you hit it. The physics definition of a force is a push or a pull. So a force is either a push or a pull. Okay, and there are two kinds of forces. There are what are known as contact forces. So a contact force is one that requires touching. That would be hitting a baseball, catching a baseball, right? You can't do any of these without touching it. And there are a non-contact force is a force like gravity. It can act at a distance, and it doesn't require physical touching. We're still not sure why or how gravity works or magnetism work, but these are non-contact forces, and right now a lot of physicists are spending their time trying to figure out why gravity can affect the Earth from such a great distance, or why magnetic force exists. A force can also cause a change in an object's velocity. In other words, a force often leads to an acceleration, right? Remember, acceleration is the change in either the magnitude or the direction. Okay, so we think of here the girl is throwing the ball, so she's changing the magnitude of the velocity. She's giving it a greater velocity. Here he's stopping its velocity, right? But here is an example of a change in direction as well as a change in magnitude. But all three of these cases are a force is causing a change in velocity or an acceleration. So in this video, we're going to watch what happens when a baseball and a baseball bat hit at very high speeds. And it's very interesting physics, but it'll help illustrate how forces are used to change the direction and the magnitude of an object's velocity.
Time warp. A baseball bat is one tough item, but how tough? What really happens when bat meets ball? And why does the bat sometimes break? Even the Time Warp Lab has its limitations, so we decided to pay a house call to another lab.
This is the only place in the country where you certify the bats and the baseballs in the major leagues.
Welcome to the University of Massachusetts Lowell Baseball Research Center. Here, Patrick Drain will show Jeff and Matt the scientific reason for broken bats. And to do so, Patrick uses this crazy machine.
What we basically have here is we have a bat hanging here vertically. We're going to fire with an air cannon a ball at 160, 180 miles per hour and see what the collision looks like and go from there.
We're loading the machine with a regulation wooden bat made of ash, a longtime favorite in the big leagues.
That's way too fast to see.
Now to whip some ash, Time Warp style.
Okay, that's...
So what you can see in that part of the video right there is that the bat is applying a tremendous force to the baseball in this direction, right? So the force is in this direction, and you can see it's such a tremendous force that the shape of the baseball and the shape of the bat are even transformed at that moment. So right at this moment, the bat is applying a huge force to the ball. Let's go back to that. So we can see right at this moment, you can see the ball and bat have met, and now to change the direction of the ball, to get the ball to go back in this direction, the bat exerts a force on the ball, and it's an extremely high force because we can see it transforms the shape of the baseball even as that's happening. So that's what a force is. That's interesting. And if you play baseball, this is why aluminum bats tend to be much more, it's much better to hit the ball with, because the bat itself doesn't deform, so it can give a much greater force to a baseball. Unit of force that we use, the SI unit of force, is the Newton, and it's abbreviated with the letter N, and it's named after Sir Isaac Newton, who was a 17th century physicist who is considered by most scholars to be one of the most intelligent people that ever have walked on the earth. So very interesting. We'll talk a little bit more about him in some later videos. Okay, so there are different units of force that are used around the world. Most countries which use the international system, or System International, the SI unit, is newtons. That's the unit for force. There's something called dyne, and then of course in America we use the pound. So and there's only 3 countries in the world that use pound. So this is kind of funny. Here's the map of the world, right? The only 3 countries that use the pound: America here, a country in Africa called Liberia, and Burma, which is in Asia. Everyone else in the world uses the metric system. So take that for what it's worth. But we're in America, so we do deal with pounds. You might wonder, and if you can talk about, where does the word pound come from? It actually comes from the Latin libra, right, which is which means to weigh, and we use the abbreviation LB. So if you ever wonder where LB comes from, it's from Libra. Some of you have an astrology sign that is Libra, which is interesting. The connection between newtons and pounds is a simple conversion. This is a very useful conversion factor. So 1 pound is equal to 4.48 newtons. Okay, so this is a conversion that we will use frequently as we're converting back and forth. Okay, so remember that force is a vector. Direction matters, right? The direction in which I push or pull something is going to affect the direction it moves. So since force is a vector, we can represent it with our vector arrows. And we are going to learn to draw in this video and then practice in the next video what are known as free body diagrams. Sometimes I will abbreviate these as FBD. So if you see me say FBD, I'm talking about a free body diagram. And a free body diagram helps analyze a situation that deals with forces. Let's take, for example, a car that's hitting a wall like this. So we draw the forces that act on each object on that object. So for example, there are 3 forces acting on the car. The first force is the force of the wall on the car, and that is pushing the car back, right? When the car hits the wall pushes back on the car. That would be this force. And on a free body diagram, I would like you guys to label the forces. So actually, if we zoom in here on this, I'm going to label this force is the force of the wall on the car. This downward force, this is the force of gravity on the car. So this is the force of gravity on the car. And then the upward force is the force of the floor on the car, right? So this is the force of the floor on the car. And we're going to use our same nomenclature that we used before for relative motion with the subscripts, right? Since force is a vector, we're going to give a little arrow above the F's there, okay? And in our next video, we'll practice drawing our free body diagrams, okay? So that's an introduction, and I hope that makes sense. If you have any questions, as always, email me, let me know, and have fun.